So we're going to learn a teeny tiny bit about organic compounds. The name organic came from the original division that the early chemists made. Compounds that came from living organisms and compounds that came from non-living things. So organic compounds came from living things. They observed general properties about these two types of compounds. Organic compounds were a lot easier to decompose or destroy than the inorganic ones, but the inorganic compounds were a lot easier to make in a lab. Making sodium chloride isn't that hard. Making ethanol is more difficult to do in the lab. Of course, today we can make pretty much anything. And so organic in chemistry does not mean naturally occurring. Organic things are not necessarily safe, right? We have this warm, fuzzy feeling about organic fruits and vegetables, right? But organic compounds in chemistry are actually some of the more dangerous compounds. So organic compounds have carbon in them. Carbon and hydrogen. There can be other elements. The common ones are oxygen, nitrogen, phosphorus, sulfur. There can be other elements as well, but it's the carbon and hydrogen that are the main part of organic chemistry. So carbon is the key element, and if you watch, science fiction movies, they talk about carbon-based life form, right? We are a carbon-based life form. All of our organic compounds are based on the chemistry of carbon. Now, in theory, you could have something similar to this in, say, a silicon-based life form. Nobody's discovered anything like that, but, silicon has similar chemistry, and so it might be possible. But this is based on carbon. So carbon always makes 4 bonds. And so here we have a structural formula. This is the smallest organic molecule, methane, which is in natural gas, CH4. Here we have the space-filling model. Carbon bonds in organic chemistry are covalent. So they're always shared. And carbon forms 4 covalent bonds. Those can be single, double, or triple. So it could have 3 triple bonds and 1 single bond, or 2 double bonds, or a double bond and 2 single bonds. Any combination, but it's always 4 bonds. And these bonds can be with other carbon atoms or with different elements. And what makes this chemistry so interesting is that carbon is able to form long chains, and it can form branch chains, some very complicated things, and it can also form ring structures. And so then with just the 2 elements, carbon and hydrogen, and you add in the different bonding patterns and different types of bonds, and you get a whole mess of compounds that are possible. So here's a few examples. So here we have, this one has 3 carbons. They're in a chain, we call it a chain, and then around them are the hydrogens. And it's very nice to draw because the carbon needs 4 bonds, and so we can make it square here, and we just would fill in with hydrogens so that the carbon has 4 bonds. So this is what's called a straight chain. Here, this one has 4 carbons, but instead of the 4 in a straight line, a straight chain, this one has a branch in it. So this carbon is stuck to the middle here instead of being on the end, which also is another possibility. So that's a branch chain. This is a ring structure. We have 6 carbons, and instead of in a long chain, they've joined in a circle, play Ring Around the Rosie or something. This is an example of one with a double bond. So here the 2 carbons have a double bond, and that means there aren't going to be as many hydrogens because this carbon only needs 2 hydrogens to make up its 4 bonds. Here we have one with a triple bond. You'll notice each carbon still has 4 bonds. Here we have one where we've got oxygen in here as well. So this carbon has a double bond with oxygen, a single bond with this oxygen, a single bond with that carbon, still has 4 bonds. Over here, this is sort of a shorthand way of drawing this piece on the end. So this part here is often abbreviated as CH3 or H3C, if it's depending on which end it's on. Yeah.
The prefixes iso and cyclo, do those refer to the branch chain and the ring structure?
Yes. The prefixes, the prefix cyclo means that the carbons are in a ring, and iso is iso is a prefix that means the same, and so isobutane is a branched form of butane. Yeah. And so there is a whole system of nomenclature for organic chemistry, which is actually one of my favorite parts of organic chemistry, because it's like a problem, and you get some big hairy ones, and then you can argue with each other about which rule comes first. And it's just very nerdy stuff. So organic compounds all have a single systematic name, and then they also have common names, right? And so, like, you see a drug like ibuprofen. Ibuprofen is the common name for that molecule. The molecule's actual name might take up 2 lines, on notebook paper, because you have to describe all the little things. So chemists categorizing things again. So here we have all the compounds, which, is separate from the elements and mixtures. And in all the compounds, we have inorganic compounds, which is what we're talking about in Chem 1A for the most part. And then we have organic compounds. And these can be divided into hydrocarbons and functionalized hydrocarbons. Hydrocarbon, as the name suggests, contains hydrogen and carbon. Hydrocarbon, just carbon and hydrogen. There's a whole group of those. Functionalized hydrocarbons also have hydrogen and carbon in them, but there's something extra about them. So hydrocarbons are commonly used as fuels. They have high chemical potential energy, so when you burn them, you can get a lot of energy out. Oil, gasoline, liquid propane, natural gas, all of these things are hydrocarbons. When they burn, they give off carbon dioxide and water, so those are not harmful. We don't want too much CO2 in the air, but it's still not anything bad. The pollution from the combustion of these things comes more from trace quantities of other stuff. So these are oil and gasoline are typically obtained from fossil fuels. So when you take this crude oil that's got all kinds of different things, and you get this big refinery, and you're separating out the different parts. Can you separate it out so that you get pure octane? Yes, you can. Octane burns really well in a car engine. But the cost of getting pure octane to use as gasoline is prohibitive. What does the train run on? They use diesel? Just diesel? Yeah. So one of these. A train out there burning hydrocarbons. Yeah. Are you done? I think he's done. So we could purify them, but it would cost so much that we wouldn't be able to drive our cars. And so we purify it enough, so it's a kind of a compromise. But like the NO2 emissions and all of those things that come from your car, those are impurities in the gasoline. It's not from the gasoline itself. So for those hydrocarbons, we can divide these into 3 groups based on the kinds of bonds that they have. So the first group, alkanes, only single bonds. All the bonds are single bonds. And then there's a group called alkenes. These contain at least one double bond, and alkynes contain at least one triple bond. So the naming here is you have a base name that's determined by the number of carbon atoms, and then a suffix that tells us what kind of bonds there are. And so the suffixes are -ine, -ine, and -ein. So here are the suffixes, types of bonds, and it's the same ending of the name of the family, alkane. All of these end in -ane, alkenes end in -ine, alkynes end in -ein. Now, how do we indicate the number of carbons? Oh, I just realized it's not the number of hydrocarbon atoms, it's the number of carbon atoms. Well, if you skip the first four, starting with 5, those should look familiar. Pent, hex, hept, oct, non, dec. Those are the same as the prefixes we used in molecular compounds and in hydrates. It's just they don't have an A on them. And so we take a name like hex and we put ane on it, hexane. That's a compound that has 6 carbons, and they're all the bonds are single bonds. If I have pentene, that's going to have 5 carbons and at least 1 double bond. I'm giving you just the very top layer of nomenclature. It gets much more complicated very quickly, but we're just learning the super, super basic stuff. So what about these first 4? Those are historical names, and so we just have to learn to deal with them. And the way I remember them is this silly sentence, Mom eats pickled bananas. Just makes you think that Mom might be expecting another sibling for you, but Mom eats pickled bananas. So how does that help? It's the first letters. So mom, meth, eats, eth, pickled, prop, bananas, bute. 1, 2, 3, 4. And to this day, if I look at something that's got 3 carbons, I'm thinking, Mom eats pickled propane. It works. If you have another way, go for it. So here's some common hydrocarbons and their common uses, and these are just to show you things. You don't have to memorize any of these. So here we have methane. So the prefix meth says 1 carbon. The suffix ane says there's only single bonds. And when we look at this structural formula, 1 carbon, all single bonds. Here's propane. Prop is the prefix meaning 3. So here we have 3 carbons. Again, all single bonds with the ane suffix. So we put hydrogens around so that all the carbons can have 4 bonds. Yeah.
So when we're figuring this out, we would draw it out, right? That would be the easiest way to...
That would be the easiest way, yeah. You can, so this is a straight chain, and the N-butane, N stands for normal, and it means a straight chain. We are only going to deal with straight chain hydrocarbons. So knowing that, C4H10, the C4, you can know that that's going to be butane. Now, does it have any double bonds or triple bonds? Then it's easiest to just draw it out. So this is four carbons in a line. Then there's N-pentane, so that's 5. Here we've got ethene. So eth is the prefix for 2 carbons. 2 carbons. The ene says there's a double bond. There's only one place it could be on this one, so there it is between the 2 carbons. And then here's ethyne. 2 carbons again with a triple bond instead. So then they each only have one hydrogen to make up the 4 bonds. So you get that kind of the idea of this. The functional group are called functional groups because it adds a functionality or a different chemical property to the compound. You could call double and triple bonds functional groups because they do cause those compounds to react differently. But we're going to focus on the regular functional groups. So if you have a group of organic compounds that have the same functional group, we say they're in a family because they have this group in common. So here are two members of the alcohol group, the alcohol family, methanol and isopropanol. So methanol, the prefix meth says 1 carbon. And then the name is changed because there's a pattern to name alcohols. And down here we have propanol. There are 3 carbons. So that's where the prop comes from. And again, the anol part is for alcohols. The nomenclature here gets a little different because now we have to specify where is the OH functional group. This is the alcohol functional group. So here in blue, it says this is the hydrocarbon group, or R. So we can abbreviate this as ROH, and down this one would be also ROH, where R stands for hydrocarbon. Any combination or arrangement, carbons and hydrogens. And so what these have in common is this OH group. So here are the main families. And the good news is you don't need to know all of these. I want you to be able to recognize the alcohols. So that's going to be hydrocarbon with an OH on it. Then there are ethers and aldehydes, ketones. And then carboxylic acids, I think, are more useful than some of the others. In the carboxylic acid, you have this OH as you do in an alcohol, but you also have an oxygen double bonded to the carbon here. And then there's esters and amines. Amines have nitrogen in them. In a way, you can think of them as being substituted ammonia. So this is like ammonia, NH3, but instead of one of these H's, a third H here, you've got an R group, a hydrocarbon group. So these are the 3 I want you to be able to identify. And I picked these because I know a lot of you are also taking biology, and these are more important biochemically. Any questions? So what kind of a question might you have to answer on an exam? You can also look at the practice questions. This will not be a big part of the exam. But we should be able to do this. Draw the structural formula for nonane. Well, what does the prefix non mean? 9. So 9 carbons. And this will give you an example of the type of math you encounter in organic chemistry. 1, 2, 3, 4, 5, 6, 7, 8, 9. So there's 9 carbons. And then that ane suffix says they're all single bonds. So I don't have to put double bonds anywhere. And then how do I know how many hydrogens to put on here? Each carbon has to have 4 bonds. So I can draw bonds at right angles so I can see. So I need a hydrogen at the end of each of those lines. And you can see how that could get really tedious. So there are many other ways of representing this molecule that don't involve writing out all the H's. But that's no name. What if we were trying to do no neen? What's that "een" mean? Double bond. So this isn't a real complete name, but draw a no neen. You can do that. There would be lots of different correct answers. What we need to do is put a double bond. Let's just put a double bond on the end. So make that into a double bond. But the carbons can only have 4 bonds, right? So that means I have to take off a hydrogen here, so that carbon has 4 bonds, and I have to take off a hydrogen over there, so that carbon has 4 bonds. The rest of it's the same. You could put that double bond anywhere in that compound. Any questions?
So the suffix is just telling us that there's one double.
The suffix "een" tells me there is at least one double bond.
Okay.
So it gets complicated fast, because then what if you have double bonds and triple bonds? Which one takes priority? And so then, yeah, it gets
We
very
don't have to
interesting.
worry about that.
You don't have to worry about any of that. No. If I gave you this formula, I would expect you to choose nonene as the name, as opposed to nonane or nonine or octane or octene. So you have to count the carbons and get the right prefix. So this one down here, I wouldn't ask you to name because I haven't taught you how to do that, but I might ask you, what family does this belong to? So the amine family has nitrogen in it. The alcohol family has just the OH group on it. This one has an OH and the double bond oxygen. So this is a carboxylic acid.
What does the YL mean?
In carboxylic,
Or just as a suffix in the future?
well, it's a carboxyl group, which this is the carboxyl group. It depends on what it's attached to, but it generally implies multiple bond as opposed to all single bonds. So this is a carboxylic acid. That is also a carboxylic acid. What's the formula for that? Well, there's 2 carbons. And how many hydrogens? 4. And how many oxygens? 2. C2 H4O2. We more commonly write that as HC2H3O2. That's acetic acid. This hydrogen is the hydrogen that gets lost. An acid is a molecular compound that ionizes when you put it into water. So when I put this molecule into water, this hydrogen comes off. And what's left is the acetate ion. So I'm not going to expect you to remember that, but I'm just showing you that this is one of the compounds we actually already know.